All right, we're in business here. Yeah, I'm recording. So I have a couple of things here for you. The first is, let's see, your quizzes. I did grade those, so I'll hand those back. I'll do it as I've been doing. I'll just pass around the stack. I did ask, no one objected to that last time, so I'm assuming that's still okay. There are also some quiz ones in here and a couple of quiz twos. So, yes.
I have a question. So, in doing the homework, one of the things that I found useful to print out was a list of derivatives. You will not allow that on.
You're allowed to have that list right there.
Right. This is a more comprehensive list of the written functions. Let me see. Yeah, I didn't see that one.
That's all on it. Yeah, if you get to page 5, here we go. So you've got all the trigs, all the hyperbolic trigs, all the inverse hyperbolic trigs. This one doesn't even have the inverse hyperbolic trigs, so that's actually a little more. Okay, so that's the first order of business, is getting that back. Next order of business, any questions over substitution? Everyone had an opportunity to get themselves acquainted with that technique? No questions? Okay, next thing I have is a handout. I have this page printed out for you, so I'm just going to hand it out. Save us a little time. Y'all hear that beeping noise? Ah, that was it. Okay. You didn't hear it?
I didn't hear that. I hear like a buzz.
I heard like beep, 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 beep. All right, here we go. Integration by parts. So just keep it back there. It's fine. The technique of substitution. Hopefully, if you've done a lot of these problems, you realize that they can get kind of complicated. But at the end of the day, it's seeing something in its derivative, or just trying something, right? I mean and you have to have tried at least 40 or 50 of these, I think, to really feel comfortable with it. So hopefully you've gotten there, or by the end of the weekend you'll be there. Now we start this next technique, integration by parts. It's a very powerful technique. It can't be used on everything, but it can be used on certain integrals that you cannot use substitution on, and you cannot use just power rule, just basic stuff. So I talked about the formula last time. I showed you where it came from, and here's the formula written down again. And what we want to see is that with integration by parts, you start with an integral, right? You start with this integral, and it has some function and then some other function. And that when you change it using the formula ultraviolet minus voodoo, whatever's over here, the dv, gets integrated over to the new integral, and whatever was u gets differentiated over there. So the idea is that you start with an integral and you change it into something minus a new integral, and you're hoping that that new integral is easier to solve than the original one. That's the idea. You're hoping that what's in that new integral is better than what you had to start with. So I have this first example we're going to do. And I left that piece of paper, I printed that out for you so you could fill it in as I go through this. And I'll first point out that we have the integral x sine x dx. So you might first look at this and say, okay, is there a basic substitution? Do I see something in its derivative? Well, do you see something in its derivative? Not really, right? I mean, what are you going to try? Maybe sine x? But the derivative of sine x is cosine x. You don't have cosine x. You have an x up there just by itself, but then I said never make a substitution of u equals x, right? So you can't do that. Also, I put up here, be careful. Do not split this integral up. I've seen that happen many times. Students will just kind of lose track of things, go, oh, wait, hey, I know how to integrate x and I know how to integrate sine, so I'll just integrate them separately. You can't do that. You cannot integrate a product by integrating each of the factors. So be careful. Don't do that. So what we need to do, if we're going to try and use integration by parts, is we need to choose, by looking at this integral, what's going to be our u, what's going to be our dv. And in this particular problem, we really only have two practical choices. We can look at the integral and say, all right, I'll let my x be my u, and I'll let my sine x dx be my dv, right? That okay? Now, I said don't ever let u be x, right? Didn't I? But this isn't substitution. This is integration by parts. It's a different technique. So that rule does not apply to integration by parts. All right? You can let u be x in integration by parts, just not in basic substitution. So that's one way I could look at it. I could have rearranged it a little bit, and I could have looked at it as the sine being my u and the x dx as being my dv. Now, I set up this table, and that's the way I'm going to do all my integration by parts. I'll use a table. And so here's two different scenarios. In this scenario, I would need to figure out what happens to u. And what does happen to you back up here on this formula? What happens to you in the new integral? I differentiate it. And then what happens to the dv? I integrate it. So the way I have my table written, the arrow coming down means I'm going to differentiate, and the arrow going up means I'm going to integrate. So let's differentiate u. What's du? Du would be dx. Now, yes, you could say 1, but remember, the left side is actually du dx, and then you'd multiply both sides by dx. So it's important to represent the 1 as a dx. Is that all right? Now, what's the antiderivative? So we're going on the other one here. What's the antiderivative? Go up, and that should give you v, shouldn't it? What's the antiderivative of sine x dx? Negative cosine x. Okay, does everyone see that? No questions? Now that's if we had chosen it that way. Let's go look at it and see if we had done it the other way. If we did it the other way, we would have du, which would be what here? Cosine x dx. You'll always have that dx there when you take a derivative. And then on the other one, the x dx, when you integrate that back up, you get what? V equals x squared over 2, or 1/2 x squared. So my question to you now is, which one of these two approaches makes more sense? What will the new integral look like? And can you evaluate that new integral? So in the formula for integration by parts, what am I going to wind up integrating? Look back up here at the integration by parts formula. The new integral is going to be v du, isn't it? V du. So looking off this table, here's v, here's du, right? So that integral would be what? Integral, I'll write it down even though I normally won't. It'll be integral negative cosine x dx. Can you integrate negative cosine x dx? Very easily, right? That's just a basic formula. The antiderivative of cosine x is sine x. The negative comes out as a constant. That's a very simple integral, isn't it? So what would happen in the new integrals, it would be something we like. Now let's compare that to the other one. On this side, our new integral would have become v du, right? V du, so that would be this piece right here times this piece in my integral, which is 1/2 x squared cosine x dx. What do you think about that integral? Much more complicated, isn't it? That's actually worse than what we started with, because we started with x sine x. Now we've got an x squared and a cosine x. So that's even worse. Would you agree? So which of these makes more sense? This one. So the way that you pick your u and your dv to start the problem is critical. And you might have to look at different options. But what you want to get to is a point where you look at the problem and you see it. You go, I see what my u and my dv should be. Make sense? Okay, let me see if I have space to work this problem out. I think I did it. Is it on the next sheet? No, it's not. Okay, so I'm going to work this problem out from scratch now, right? Just so we have it. Here we go. Let me move this page. All right, so to start out, I have the integral x sine x dx. I'm going to use integration by parts. I'm going to write that down. I BP. That's just letting whoever's reading this know that's what I'm about to use. I'm going to make a table. I'm going to have to choose a u, and I'm going to have to choose a dv. What do you prefer? Whatever. I'm not going to take points off. Nope. The book doesn't do a table, but they do write u, du, and dv. So it's up to you. But I do want to see what your u is and what your dv is. All right, so we chose, what was our best choice? X, right? And over here, du was dx. And v here, dv was sine x dx. And then up here was negative cosine x. Now we know that the new integral, right, this will turn into ultraviolet minus integral voodoo, VDU. So let's go ahead and write it down in terms of what we have. This would be equal to, what's ultraviolet for us? It's the u times the v, so it's x times cosine, negative cosine x. So I'm just going to put negative x cosine x. That's ultraviolet. Minus integral v du, which was negative cosine x dx, which equals negative x cosine x. Negative and negative is positive, so plus integral. I'm going to go one more step. I just factored negative out. That's fine. And this becomes negative x cosine x. Now take your antiderivative, plus sine x plus c. So no more integral because the antiderivative of cosine is sine. That's it. That is your antiderivative. Now, how would you check to see that this is correct? This is the antiderivative, right? Take the derivative. Take the derivative of this. Take derivative. So I'm going to do that just to check it, just so you can see how great integration by parts is. I mean, it gets you what you want. If I take the derivative of this, I have a product rule here. All right? I have to do a product rule there. The sine I can take derivative of right away. It's cosine. Derivative of c is 0. So let me just do this product rule real quick. The derivative of negative x is negative 1 times the cosine x plus derivative cosine x, which is negative sine x times negative x plus, now derivative of sine is cosine, plus derivative of c is 0. That's what you would get. Now, this and this cancel. And negative sine x times negative x is positive x sine x, which is the integrand. That's what we were trying to integrate. So it checks. Okay? So it's a very nice method, obviously. Questions on that? Just to check. Yeah, just to check. Anytime you have an integral and you get an answer, you can differentiate it, and it should be the integrand. That's how you would know it's the right answer. All right, now I think on the back of that page, I put one more. And I have like another 8 or so we're going to do, but I didn't give you a handout. All right, so what would be your first approach on this? Yes. Where are those extra handouts? Anyone else need a handout? You got one? Okay, so now hold on. Before we start going integration by parts, you want to start thinking about these integrals in general. Like, if you didn't know this was an integration by parts problem, the first thing you would try and do is a substitution. Let u be something. Natural log x, then what's du? 1 over x. Do you have a 1 over x? Well, no, I'm saying thinking about it in general now. So you have to imagine that when you get to an exam, I'm not going to tell you this is integration by parts. So what's your method? You always want to look for a basic substitution first. Always. Of course, if I tell you do this problem with integration by parts, then the first thing you would do is try and find a u and a dv. But that's not, I mean, calculus would be easier if they always told you for the integral what method to use. That's not the way it is. So I look for a substitution here. I don't see anything obvious that it's a u du, so I go to my next tool in the bag, which is integration by parts. And so I look, can I choose a u and a dv? Keeping in mind that whatever I choose for u, I'm going to differentiate it. Whatever I choose for dv, I'm going to integrate it. So let's try. Someone give me a u that you want to go natural log x, okay? And that would force me to use what as my dv? Everything that's left. You have to account for everything in the integral, okay? Everything has to be accounted for. So my x to the 4th dx accounts for this part. My natural log of x here accounts for this part. So everything's accounted for if I do it that way. Now let's go ahead and find what the du and the v would be. So what would du be? 1 over x dx, because the derivative of natural log x is 1 over x. Now I need the antiderivative of x to the 4th. 1 over 5 x to the 5th. The reason why I do a table is just because it keeps my thoughts organized, but it also, I know that if I do a table, these two that are across from each other diagonally, that's my new integral, right? Voodoo is always that diagonal. And so when I look at voodoo, 1/5 x to the 5th, and I multiply it times 1 over x, I get what? An x to the 4th, which is just a power of x. Can you integrate a power of x? Hopefully, right? Hopefully you're at that point. So that looks like it's going to be the winner right there. But let's say that you had done it the other way. What would the other way be? I choose my x to the 4th to be my u. My du would be 4x cubed dx. Now, my only choice, if I do it that way, my only choice, that's not working very good. If I choose my x to the 4th to be my u, then my dv must be what now? ln x dx. And here you're going to run into a wall. Because what's the antiderivative of the natural log? Antiderivative, not derivative, antiderivative. We actually don't know that, and we're actually going to find it in the next problem ourselves. But right now, we can't go backwards up to natural log x. I mean, integrate up. Okay? So we would be stuck here. So that kind of forces us back to this one, doesn't it? Now, from this, I don't want you to get the idea that with every problem, you're going to look at the different, like I could do this for you or this. That's not it. You want to do kind of one at a time, just attack it, and if it doesn't work, maybe then you do another one. But I just want you to see how you set these up. All right, so I'm going to go with this first one. I'm going to rewrite this integral as ultraviolet minus integral voodoo, which turns into Ultraviolet would be what? Good. 1/5 x to the 5th times ln x. I always put my polynomials in front of my transcendentals. And then minus integral v du. 1/5 x to the 5th times 1 over x dx. Just cleaning up now. This is the 1/5 can come out. I have x to the 5th dx. To the 4th, thank you. And the integral of x to the 4th dx is 1/5 x to the 5th. So I'm ready to take my antiderivative there. So I'll have 2 1/5ths, won't I? So minus 1/25 x to the 5th plus c. You could check that. You would have to do a product rule on the first part and then the next two terms. Questions? No? In your integrand, where, yes, you can have some pretty complicated stuff in there, where you don't have, it's not obvious just this one or this one. We'll have an example of something similar to it in a little while. Next one. Okay, this one you don't have, right? I didn't print this one out for you. So let me do it this way. I'm going to take away the or. Well, I guess so. I'll leave it, I guess. So now let's talk about the antiderivative of natural log of x. Everyone knows the derivative of natural log of x is 1 over x. But what about the antiderivative? If you look on your formula sheet, is this on your formula sheet? It's not for integrals? Probably isn't. For integrals, no. Okay, but this is one that I'm going to let you write onto your formula sheet because it comes up a lot. So you'll be able to add this to your formula sheet after we prove what it is. All right, so what about your choice of u in dv here? Obviously, substitution's not going to work, right? Basic substitution. So what are your choices for u? Yeah, I mean, you don't have a lot of choices here, do you? Right? ln of x. So I could use ln of x, which would force my dv to be what? dx. Now, I want to see if anybody could have given me a different alternative. Can somebody tell me what I also could have chosen for u and dv? 1 for u, and then dv would have to be what? The rest, which is? You could do that, but what's wrong with that? Look at what you have to do to go from dv back up to v. Isn't that the original problem? Isn't it? So there's no way you're going to do it because, I mean, that's what you're trying to do to start, right? But you could break it up that way. I just want you to see that you could have. It just won't go anywhere. So this is gonna fail. So our only real choice of u is natural log x. So let's finish off this table. du is 1 over x dx. And now be careful here. dv is dx. That's like 1, right? What's the antiderivative of 1? X. So v is x. And when you look at it this way, voodoo, when you multiply those two together, is that going to be something you can do? It's just 1. You can take the antiderivative of 1, right? So this is going to work out good. It's going to work out real good. Let's rewrite it. This should turn into ultraviolet minus voodoo, integral voodoo, which for us is ultraviolet. What's that? X ln x minus integral. Yeah, I'm going to write it, but yeah, that's where we're going to go. You don't have to write it like this in detail. Like you don't have to put the x 1 over x. I just want everyone to see that's the v du. This is x ln x minus 1 dx, right? And the antiderivative of 1 is, with respect to x, is x plus a c. That's your formula. And if you don't believe that that's the antiderivative of natural log of x, differentiate it. It is. You'll use product rule on x ln x, and then minus derivative of x is 1, and then things will cancel, and the only thing left will be natural log x. Can y'all like appreciate, I guess, the power of integration by parts? I mean, you look at natural log of x and you say, what's its antiderivative? You can't just look at that and be like, oh, yeah, it's x natural log x minus x. Sure. It's not like substitution where it's just obvious sitting there, you know? Substitution, a lot of times you can see it. Oh, there's its derivative. Yeah, I can see that. This one, it's much more difficult. I thought y'all would like this more. I'm not getting that feeling. Okay, how about this? Now we start to turn the screws a little bit. Where does that phrase "turn the screws" come from? I think I know, but I'm not sure. What is it? It's Inquisition, right? It's where they used to torture you and they would turn the, whatever, compressing your head or whatever it is, stretching your body, they turn the screw just a little more. So that's what we're doing here. We're turning the screws. At some point, I'm going to stop drawing these little tables of ore. It's just going to be, here's the problem. But I'm trying to get us still in that mindset of, okay, maybe there's a few ways I could approach this. So what do you think for you? X squared? Okay. Or you could have done u as what? E to the x, right? Or e to the negative x? Okay, let's just jot those down. Let's do the x squared first. Let's fill the whole table out. If that's x squared, then dv would be forced to be e to the negative x dx. The derivative of x squared is 2x dx. And now I need the antiderivative of e to the negative x. Now, I've said coming into class, I hope that you've done 50 problems of substitution. Because if you've done 40 to 50 problems of substitution, the antiderivative of e to the negative x should be trivial. Should be. It should be negative e to the negative x. Because you have a little bit of chain rule in there because of the negative up on the exponent. So you see that this one little piece of the problem now is something that we should have already resolved, like we should be comfortable with. And it's going to continue to be like that. These little integrations up within our box here are going to require some knowledge of our basic integration techniques. All right, so I'm going to leave that table for a second. I'm going to write down, okay, this is what I would have. That would be my V. This would be my du. So my voodoo. I don't know about that voodoo. Let's look at our other option maybe. Maybe the other option would have been better. We said that u could have been the e to the negative x, right? And then our dv could have been x cubed, not x cubed, x squared dx. Do you all agree with that? Okay, what would du have been over here? Negative e to the negative x dx. Because the derivative of e to anything is itself times the derivative of what's up there, which is negative 1. So that's where you get the negative e to the negative x. And then you need v. So antiderivative of x squared is 1/3 x cubed. So let me look at voodoo here. Which of those voodoos looks like it's doable? They both don't look doable, do they? But one looks worse than the other, right? The one on the right looks worse than the one on the left, doesn't it? Because you got an x cubed in front of that e to the negative x. This one, you'll have what? An x? I mean, forget all the constants and stuff. So what do you think? Does anyone see what's going to happen here? Let me go with the left one, okay? Let me go with the left one because I'm just instinct hopefully is guiding us to say that one looks nicer. Tell me what this new integral would look like. And I'm not going to write ultraviolet minus voodoo anymore. What would ultraviolet be? Negative x squared. So this equals negative x squared times e to the negative x. And then I'm going to have an integral. Let's get the sign taken care of. It would have been minus, but what am I going to factor out of voodoo? Negative 2. So that's going to become a plus 2 out here, right? Is that okay? I'm showing less of the work here, but I don't want to go too far if I lose people. What I did there was the negative and the 2 come out. Since they come out and there's a minus out there already, it becomes minus a negative 2, so plus 2. What's still in the integral here? X e to the negative x dx. But we don't know what the antiderivative of x e to the negative x is, do we? Another round of integration by parts. We're going to do integration by parts again. Because what's happening is that in my first application of integration by parts, what happened to the power on x? I started out at where? My original integral started out with a power of x squared in front of that e to the negative x, right? In one round or one application of integration by parts, I've reduced the x squared to an x. And if I do it again, I'm going to reduce the x to a 1. Remember the whole idea that I was trying to get you to think about last class and the beginning of this class, transferring of the derivative. One of these gets differentiated, one gets integrated. So if you have a power function, x to a power, each time you apply the integration by parts, the power is going to drop, right? Each time. So if that were an x to the 7th, we might have to apply integration by parts 6, 7 times to get it to finally vanish. The integration on the other one doesn't matter because every time I integrate it, what am I going to get? The e to the negative x. It's just going to be itself. I mean, we're going to have some sign changes, but every time I integrate e to the x, it's going to become e to the x, e to the negative x. Do y'all see that? That's the big picture here. You want to, ahead of time, see this sort of thing happening. All right, so how am I going to do integration by parts again on this? Well, first of all, I'm going to focus all my attention just on this integral, right? That's it. I want to remember that my answer has negative x squared e to the negative x plus 2 times whatever I get now. So I'm going to come in with a new table. It is okay to use u and dv again, as long as you don't confuse it with the u and dv from before. But notice our integral doesn't have a u and a dv, right? It doesn't have the variables u and v. So I can still use u and v. So I'm going to choose a u and I'm going to choose a dv on my second application here. I choose u to be what? X. And dv to be e to the negative x dx, right? du then becomes dx, and v is negative e to the negative x. Then my new voodoo is just what? What's my new voodoo? Negative e to the negative x, but I no longer have an x in there. And so it's just basically the antiderivative of e to the negative x, which is going to be easy for us to get. Easy, relatively easy, right? So what does this one integral become? I'm going to come back up here and kind of circle this here. Whoa, shaky. What does just that become? Ultraviolet, right? Negative x e to the negative x minus integral. Well, is it going to be minus integral? It's going to be plus because of that negative that was sitting in front of the e to the negative x. And then what's still in here? E to the negative x dx. But that is negative x e to the negative x. What's the antiderivative of e to the negative x? Negative e to the negative x plus a constant. And now this part right now here is ready to be pasted back into where we were before. So I've got to bring this thing down. I'm going to zoom out so I can get this in here. So this now becomes equal to negative x squared e to the negative x plus 2 times, now everything I just got, negative x e to the negative x minus e to the negative x. Now watch what I do here. Close this off, plus c way out here. Why did I put a plus c way out there instead of inside the brackets? Yeah, it doesn't matter. Even if it was 2 times a constant, 2 times a constant is still a constant. I'm always going to have plus a constant. So it doesn't matter what I call it. 2c, I call it c squared. I call it pi times c. It doesn't matter. It's a constant. I don't know what it is. So I just pull it out very end of the antiderivative. Now just distribute and see if there's any like terms. See, minus 2x e to the negative x minus 2e to the negative x plus c. So I know this is very low on the page here, but any of those like terms? You have you have a common factor, but other than that, you don't have like terms. Like can't add and subtract. Most of the time, a book will do this. They'll factor out the e to the negative x and be left with like negative x squared minus 2x minus 2 plus a c. And they may even factor out the negative and make it negative e to the negative x and make it x squared plus 2x plus 2. Okay? So that is your first example of integration by parts applied twice to a problem. This is a classic problem right here. Classic meaning every Cal 2 student sees something like this. Wolframalpha. A trig function. Yeah, it has to be something that will vanish. In other words, one of them has to be a polynomial, like x squared or x cubed. Then there are little cute tables you can make that, yes. I mean, I guess you could call it a shortcut. I mean, I'm not, what's that? it's just the fact that you see a pattern that every time you do an integration by parts, that power on the x keeps going down. So there's a way you could make a cute little, I guess, shortcut. I need to see some work. What I need you to demonstrate to me is that you know how to apply integration by parts. I'm not a big fan of shortcuts unless they're shortcuts that are general. In other words, they will work for any integral. If it's just a specific case, I don't like to teach specific case things like that because it's just too narrow for me. Right? Does that kind of make sense? Okay. It's just the mathematician in me. We like to generalize. We don't like to. It's like FOIL, okay? This is a perfect example. I don't teach my algebra classes to FOIL. Because what's FOIL? X plus 2, x minus 2, something like, or x plus 21, something. FOIL is cute because it works, right? And you do this first outer inner last, everyone remembers it, cute. But then as soon as you give them something like this, what happens? They don't know what to do, right? I need 2 and 2. If I can go 2 and 2, I can do FOIL. If you give me 3 and 2, I'm done, cooked. And that's what I'm afraid of with any shortcut I ever give anyone, is that, yes, it may work for that specific case, but is that more valuable than you knowing it in general? To me, more general is more important. This example is a perfect example of why you shouldn't try and you can't always have a shortcut for something like this. See, the previous problem, we had x squared out front in front of e to the x, didn't we? X squared in front of the e to the x thing. And the first application dropped that power on x squared down to x. And the second application dropped the power of x down to 1, and then we were good. And we were good because the e to the x kept on cycling, right? Every time we took a derivative, it stayed the same pretty much. Look what we have here. We have a function, we can look at it split there. We have an e to the negative x, right? And we have a cosine 2x. Now, if we try and think of it the same way, if we do one application, and let's say we let the e to the negative x be our u. The first application, what happens to that e to the negative x? Its derivative is still e to the negative x. And then what happens with the cosine 2x? If that's dv, it goes back up to a sine, doesn't it? So now we'll have a sine and an e to the x. And so a second application, you're still going to have an e to the x, and now you're going to go from sine back to cosine. See what I'm saying? So these functions that are transcendental, when you take their derivatives, they cycle. Like the e to the x cycles through itself. The cosine cycles between sine, cosine, sine, cosine. So you're never going to get one of them to vanish. Does that kind of make sense? So they're always going to have each other there. So you sit here and go, what the hell am I going to do with it? Well, we're going to take a swing, and we're going to get it, but it's not a natural idea of how it's going to happen. All right. E to the x, natural log, sine, cosine, tangent. Okay, let's just take a swing. Let's take our u, and let's do dv. So I'm going to choose my u to be e to the negative x, and my dv to be cosine 2x dx. Now I'm doing that after having thought through this, realizing that transferring the derivative doesn't look like it's going to get me anywhere, but I still have to try something, right? So let's now take a look at du. Negative e to the negative x dx. And dv goes up to v, that becomes close. 1/2 sine 2x. That was one of those ones I showed you. I gave you that one. I gave you general formula for the integral of sine. What was it? Ax plus b or something like that. I said it's always going to be antiderivatives 1 over a cosine. Yeah, go back and look in your notes. So that, again, that integration there should be kind of clean for us. Let's look at our voodoo. Do you see how we're kind of in a tight spot here with our voodoo? Like, that doesn't get any better, does it? And now you could try a different way. Choose another U, choose another DV, and you're still going to be in the same spot. Well, you just got to try. So let's see what would happen. We would have ultraviolet. Ultraviolet would be 1/2 e to the negative x sine 2x. Right? Minus integral voodoo. So is it really going to be minus? It's going to be plus what? 1/2 integral e to the negative x sine 2x dx. So at this point, you should be somewhat discouraged. Are you okay with the fact that I put the dx way on the outside and I moved it from the e to the negative x? Does anyone have a question off any of that? UV, I put the 1/2 in front, right? And then there's U and V. I'm putting my exponential in front of my trig. And that's just kind of the pattern I'm going to continue with. It doesn't matter. You could put the trig in front of the exponential. Yeah. But you're okay with all the numbers? Yes. Because they both keep cycling, it wouldn't matter how you chose it. So if you had done U is cosine 2x and dV is e to the negative x, we could probably still achieve this problem. But it's how. So we look at this, we know that if we do integration by parts again, we know it's going to cycle, don't we? But let's try it. I'm going to do integration by parts one more time. I'm going to choose my U to be the same thing it just was, which was the e to the negative x. Going to choose my dV, choose my dV to be what was left, which was the sine 2x dx, right? Ah, man. So what's du? Negative e to the negative x dx. And then what's v? Negative, good, 1/2 cosine 2x. Now keep in mind here, all we're working on right now is this integral that I've boxed. We still have all that stuff in front of it, right? We've got the 1/2 e to the negative x sine 2x plus 1/2. Now let me just take this box down here and let's write it down, ultraviolet minus voodoo. So that's going to be negative 1/2 e to the negative x cosine 2x minus or plus? When we do voodoo, we have a negative and a negative, well, a negative 1/2 and a negative 1/2. Negative and negative are positive, right? But in the formula, the integral is minus. So this will become a minus, right? 1/2 integral what? E to the negative x cosine 2x dx. And you look at that and you say to yourself, what? Shit, right? That's the original problem. Isn't it? So you might at this point be discouraged, but watch what's about to happen. It's really nice. I'm going to rewrite this now. 1/2 e to the negative x sine 2x plus 1/2 times what I just got. Negative 1/2 e to the negative x cosine 2x minus 1/2 integral e to the negative x cosine 2x dx. Close my bracket. Yes? I'd like to distribute that 1/2 through the bracket. Now, but when I do my next line, I want you to pay attention to what I do before I distribute. Go back way up to the beginning of the problem. We're saying, right, that that integral up there in black is equal to what I'm about to write, correct? That integral up there is equal to this. So watch how I write this. The original integral is equal to 1/2 e to the negative x sine 2x plus what? Or no, not plus. I'm going to distribute. Sorry. I'm distributing, so minus 1/4 e to the negative x cosine 2x. Y'all still with me? Then what? Minus 1/4 integral e to the negative x cosine 2x dx. Yes? Anybody see it? Not cancel them. I have an integral over here that's exactly the same as an integral over there. So it's like I have, let's just say the letter u over here, and over there I have minus 1/4 u. Can't I add 1/4 of that integral to this on this side? Add it to both sides of the equation? So why don't I add over here 1/4 integral? I don't know what it is. Don't ask me what it is. I have no idea. But what I know is I can always take an equation and add anything I want to both sides. As long, any number. So plus 1/4 integral e to the negative x cosine 2x dx. Adding it on both sides, what would you get? What's one integral plus 1/4 of an integral? 1/4 of it. 5/4, isn't it? 5/4 of that integral. So all you're doing is adding the coefficients. The coefficient of the integral on top is 1. Coefficient down here is 1/4. 1 plus 1/4 is 5/4. On the right side, doesn't it cancel? Right? So what I get is 5/4 the integral e to the negative x cosine 2x dx equals what? 1/2 e to the negative x sine 2x minus 1/4 e to the negative x cosine 2x. And what would be the last thing to do then? Multiply both sides of the equation by 4/5 to wipe out the 5/4 here. So multiply both sides by 4/5. All right? Here I go. I'm going to do it. We'll be at the end at this point. So I need to go to a new page. Does anyone still need that? I can leave it up there for a second. Anyone need it? Okay, new page. It'll be grand finale here. Integral e to the negative x cosine 2x dx equals, it was a 1/2, right? But I'm going to multiply it by 4/5. What was it? What was in front of there? 5/4? 5/4? So what is this going to become then? 2/5? Everyone agree? Okay. Then what was it? E to the negative x sine 2x. And then it's minus 1/5 e to the negative x cosine 2x. That's it. Well, almost. There's something that doesn't pop out, obviously, that we need when you do this. plus c. We know that there's going to be a constant. So that was very odd, wasn't it? I mean, we didn't even get an answer. What we got is the original integral reappeared in our integration by parts, and we were able to bring it to the other side. And then we were able to get an answer. It's quite remarkable, if you ask me. So let's do something. We'll take a little mental break while I do this. Just take a breath. Everyone here loves Wolframalpha, right? Let's check our work. You did? What? Oh. Yeah. I encourage you to use Wolframalpha to check your work, but I do not encourage you to use Wolframalpha to learn, because, you know, it could be dangerous. Where's Wolframalpha? I'm taking you to the Mathematica website. They don't. Oh, there we go. Wolframalpha. They have an integrator where it'll tell you steps and stuff. So at Wolframalpha, has anyone never been here? I'm about to open your eyes to the world here. Okay, integrate. What was it? E raised to the negative x times sine 2x. Oh, was it cosine? All right, I'll have to send it back through.
How specific is Wolframalpha on your parentheses?
Very.
Yeah, it is, right?
Very, yes. So here's the answer, according to Wolframalpha. It's negative 1/5 e to the negative x cosine 2x. Is that what we had? Negative 1/5? And then if you take this is a factor distributed through the parentheses here. Negative 1/5 times negative 2 is positive 2/5 e to the negative x sine 2x. Alternate forms of the integral. Oh, here's our answer right here. Series expansion, we'll do that. Definite integral. Okay, so I think there's a way that you can actually get it to explain, right? Oh, step-by-step solution. And I think don't you have to have an ID, or yeah, you have to sign up for it. But it'll take you down, it'll show you the step-by-step of how to do it.
You get 3 step-by-steps per day if you have a free account. If you get pro, if your student's $3 a month, you have a step-by-step. Or if you buy
Yeah. So look, I'm a realist, okay? This technology was not here when I was in Cal 2, all right? It wasn't there. So I learned this the way that I envision a student should learn this. But I'm not so old school that I don't think you should use this as a tool. I'm just warning you that if you get to the point where you're like, every integral, you're Wolframalpha, show me how to do it. Yes, I get it. Go. The test, you're probably going to get obliterated. Because if someone shows you the step, that's the hard part. Like that is the part that you have to be able to do. So by I would say if you have a problem, you just can't get it. You keep on trying to work it yourself, you just can't get it. Then you go to this and look at that first step. Let me try that. Now I'll work it the rest of the way based off their first step. See if I can get it. I think that would be the right way to use that tool. Yes? Same with the TI-89. I saw the Nspire. I saw on that quiz I gave the other day, a couple of people going right to the calculator, getting the answer. Again, that's fine to check, but I need to see the steps. All right. I wish we could teach a calculus class where it was just a computer algebra system calculus class, because we would be doing some crazy stuff. if we would do a course that way. It's just that course doesn't exist yet. They don't have it where it's just, you know what, let's put the paper and pencil away. You know, here's the ideas, but let's let the computer do all the integration, and then let's do some real problems, right? Some real math, like applied math. But calculus is still what it is. So until that day comes, here's where we are. Next problem. What the heck is that? I need to move that. So what did y'all think of that problem? It's
pretty hefty.
It is, right?
Now, on the test, I think it would be probably like that or maybe more or less.
That's a fair problem on the test.
That should be worth
Be careful, everyone. This, look, I'm going to be completely honest with you. You're going to be wishing for this problem in about 3 or 4 weeks. You're going to be hoping we were doing this one instead. No, because I'm talking. This is a very fast switch into gear course. What it's kind of like in Cal 1. You wish you were just doing derivatives again, right? I mean, you wish, but at the time you may not have liked the product rule or quotient or chain. You know, it's like now it's like, God, just give me one of those. That's the way this is going to be. So I think that's what makes the class hard, is that it just picks up, it just keeps building faster and faster. All right, stick with it, everyone. Calculus 3, I've heard, there's a lot of people who think Cal 2 is harder than Cal 3. Here's the deal with Cal 3, though. The thing that you have to be good with in Cal 3 is visualization. You have to be able to visualize things in three-dimensional space. And that's where it all is. So, all right, now we have our first example of a definite integral, right, with numbers. So we're going to get a numerical answer. Yeah, yep. So the way that I approach all definite integrals when it's not just a basic antiderivative is I rewrite it as an indefinite integral first, and I'm going to figure out what the antiderivative is and then come back and plug in all the numbers. I need to pick a U and a DU, or a DV. Well, after I look at it and realize I can't do a basic substitution, right? Any ideas for U? ln x? Then that forces your dv to be what? Dv needs to be 1 over the square root of x dx. Everyone agree with that choice? I mean, does everyone agree that we could make that choice? All right. Could we have gone the other way? Could we have chosen our dv to be natural log x dx? Well, we know what the antiderivative of natural log is now, so we could actually go up, but the antiderivative is x natural x minus x. That looks a little complicated because that would be our voodoo. That would be our v. It'd be a little bit messy. But just keep that in mind. We could have chosen it the other way. And maybe because these problems seem to be getting harder, maybe that's what we're going to wind up doing. But we'll see. du is 1 over x dx. What is v? Square root of x? Close. What's the antiderivative? 2 root x. Good. It's 2 root x. Here's why. This is really, we're trying to do the antiderivative of x to the negative 1/2, aren't we? That's what 1 over square root of x is. So the antiderivative of that is 1 over n plus 1, x to the n plus 1. This is 1 over n plus 1 x to the n plus 1. So that's 1 over a half, which is 2, x to the 1/2, which is square root of x. So 2 root x. I'll leave that there. What is your voodoo going to be? Is it something you feel comfortable with? Yeah, 2 root x over x, isn't it? 2 root x over x? When you do voodoo, does that integral look doable to you? Yeah. So this should become ultraviolet 2 root x natural log x minus 2 is going to come out integral square root x over x dx. Anybody have any questions on where I got any of this? What's the square root of x over x? It's 1 over root x, or x to the negative 1/2. So I hope I can assume everyone could simplify that, right? So you should have 2 square root x ln x, square root x ln x minus 2 integral 1 over square root of x dx. I'm leaving it as 1 over square root of x because I just integrated 1 over square root of x a second ago. So I already kind of know what that is. It is what? 2 root x? 2 root x, right? But I have a negative 2 out there, so it'll become negative 4 root x plus a constant. So there's my antiderivative. But now I need to go back to the original problem and plug in my limits of integration and get a numerical answer, but into this antiderivative, which I'm going to go back up on the page and do it. Does anyone need this still? Good. Okay, so back up to the problem up here. This will be equal to, I just forgot what it was. 2 root x natural log x minus 4 root x. Do I need to put plus c? No, because remember the c's will cancel. So you have evaluated from 4 to 9. Which means I'm first going to plug in 9, see what I get, and then subtract what I get when I plug in 4. So what do you get when you plug in 9? 2 times the square root of 9, square root of 9 is 3. 2 times 3 is 6. 6 natural log 9, right? Minus 12. Now plug in 4. Square root of 4 is 2. 2 times 2 is 4. 4 ln of 4 minus 8. Which gives me 6 natural log 9 minus 4 natural log 4. Let's see, minus 12 plus 8 is minus 4. Do y'all agree with that? But this is equal to natural log of 9 to the 6th power minus natural log of 4 to the 4th power minus 4. What did I do there? Properties of logs, right? You can always take a power, pull it out front, or you can always take the number in front and push it up as a power. Why would I do that? Because my next line, I'm going to use another property of logs that says if you have 2 logs being subtracted, you can turn it into 1 log with division. So I can go natural log of 9 to the 6th over 4 to the 4th minus 4. And you can figure out what 9 to the 6th is and 4 to the 4th. And now, I personally would have been happy with an answer right here. The only reason I did the rest is because the book would probably do more and use properties of logs, and you would look at that answer and go, what the heck happened? And that's what they're doing. They're just messing around with the different properties of logs. All right, so that one wasn't as terrible as the one before, right? But just, I wanted you to see how we could, possibly have to plug numbers in. I'm going to let you try this one. All right, so you're probably going to be mad at this because it doesn't require integration by parts. And this is the challenge that I can continuing to try and stress to you, is that you do not want to get fixated into any particular technique. It's what makes integration difficult. Remember, we have substitution, we have integration by parts. We still have another 3 methods to learn. So in the big picture, you're never going to know what to attack with. So here's an approach. I'm going to look at this problem as I'm looking for something in its derivative. Well, after doing substitution for a while, you might just throw out there as just a guess, u is 4 plus r squared. Then what's the derivative of that? 2r dr. Now, do you have a 2r dr? Yes, you do. If you take the integral and rewrite it as r squared times r over square root 4 plus r squared dr. Now, do you see the r dr right there? You're just off by a half, aren't you? Now, what about the 4 plus r squared on the bottom? Well, that's just u, isn't it? The only other thing to address would be the r squared here. But how can you determine that r squared? Yeah, just take this right here, solve it for r squared. R squared is u minus 4. And now this integral becomes the r squared, which is u minus 4, over the square root of u, and dr was 1/2 du. And then what would you do with this integral? Split it into 2. U over square root of u, and negative 4 over square root of u. And then you're on your way. So, dot, dot, dot. Now, I worked this out in a video? Last spring. So, I'm saying that because if you go look at it, you can see me finish it out. I'm not going to do the rest of it. So what's the moral of the story? Yeah. Don't get fixated on a certain technique. You always start with substitution. Because in my integral, I was able to I knew that I'd be able to handle the r dr, that would be this when I divide both sides by 2 here, right? So I knew r dr was good. I knew the pink, the 4 plus r squared, I knew that would be my u, but the r squared wasn't accounted for in my integral, the blue part. So I took this one here, u equals 4 plus r squared, and I solved it for r squared by subtracting 4 on both sides. Then that tells me I can replace that r squared up there with u minus 4. I did that several times in the last class. So it might be something when you look at that. Since you weren't here last time, that's probably, if you're seeing that for the first time, you're like, what the heck? But I did do several of those last time. Okay. Sorry about that. How about this? What? This one, I don't know. What are we going to do with this one? Come on, man. What the? So what are you going to think first? Substitution. Do you see anything in its derivative? Square root of x? Maybe? What's the derivative of the square root of x? 1 over 2 root x. Do you see 1 over 2 root x anywhere? Do you see a root x in the denominator? No. What else could you try for substitution? For basic substitution or for integration by parts? See, if you have a basic substitution, if you ever, oh, that's integration by parts. If you ever just let u be x, then du is dx. Then when you rewrite the problem, it's e square root of u du. And it's exactly the same problem in terms of u. In integration by parts, okay, then that's maybe possible. But the problem here is that you don't have, remember, integration by parts says u times v. So the u you pick, if you're going to let it be x, you need to have an x being multiplied times something, which you don't have an x being multiplied. You have an x up in the exponent, but you don't have an x down as a factor. Does anybody see a basic substitution that would work? No? I don't either. Does everyone kind of agree basic substitution doesn't look like it's going to work? So that leaves us with integration by parts, and that means I've got to choose something. Oh, shoot. Hopefully that doesn't mess up the video. So, you want to go with, well, where's x though? I don't see. See, if there was an x right here, then yes, I would agree we could use x. But there's not an x there. Let's just go with this, e to the square root of x. We don't have a whole lot more to go with, do we? But that forces our dv to be what? dx. Okay, what's du going to be? Itself, e to the square root of x times 1 over 2 root x dx. And what's dv going to be? I'm sorry, not dv, v. V is going to be x. What's your ultraviolet minus voodoo? Well, what's voodoo going to be? Ooh. What is my voodoo going to be? I'll have e to the root x times x over root x, right? X over root x is root x. And you'll have it half there. Does that make it any better? I don't know. Let's see. This is going to become, I'm just rewriting this, ultraviolet minus, let's see, it'll stay minus the 1/2 is going to come out, integral. Voodoo is going to be square root of x e to the square root of x dx. So I did that a couple of steps there. I already did the x over root x. I already did that. That's here. And I took the 1/2 out of the integral. Is that all right? Did that make life any better? That integral you still can't figure out, can you? So you could try integration by parts again, possibly. Right? Didn't our integral become more complicated? But maybe integration by parts will work if I try it again. Maybe. So, do we want to try it again? Or do we want a different approach?
Well, can you use substitution for the
Okay, you want to try substitution here? Yeah, sure. Well, let's see what would happen. So we're focusing all our attention here. And you say, let's go use the square root of x. I like that. Then what's the derivative? 1 over 2 root x dx. Does everyone agree? Do I have a 1 over 2 root x? I have a root x on top, don't I? But I don't have it on bottom. So that's good, but that root x on bottom is causing a problem that I needed on the bottom. Do you want to give up on that, or you want to keep going?
Well, what I did, I didn't take the 1/2 out, and I put e to the root over x over 2 root over x, and I split it apart. So I got 1 over 2 root x, and I took u to be root of x, and I took out 1 over 2 root x.
So you didn't simplify. Okay.
And I got that as du, so then I was left with e to the u as my inside my integral.
I need to see it.
Should be multiplied by root x over root x, and then u squared over that. Then you have the dv with u squared.
Yes. Now, what I was hoping to achieve with this problem is to get you to see that, look, what's happening is that it's getting more complicated with integration by parts. We didn't see a substitution right off the bat, did we? Correct? But maybe there's something that we could do that would force this to happen. And that's what I think you're seeing, and then you're also seeing that maybe we can force it. So what I'd like to do, we could continue from here. What I'd like to do is go back. I'm only erasing because I don't want to have to write the problem over. I'd like to start off again and say, let me try a basic substitution again. And we already did this, didn't we? And the problem was that the derivative of this was what? 1 over 2 root x dx, which we said we didn't see, right? Or did we? Hell, let's throw a 2 in there. Now do you see a 1 over 2 root x in there? Do you? Do y'all see that? So I made it appear in the bottom. So let me rewrite the integral so you can just see it. I have a 2 root x e to the root x times a 1 over 2 root x dx. So I came in there with a very clever 1, didn't I? That 2 root x over 2 root x was a very clever 1 that I'm using to create the du that I need if I make this substitution. Now, can I make my substitution? What will 1 over 2 root x dx become? That'll be right here, du. What is the square root of x become? That's a u. And this is a u, isn't it? So let me rewrite the integral. It is now 2 integral u e to the u du. Do you all agree with that? Replacing everything. The 2 comes out of the integral. The square root of x is u. E to the square root of x, that's e to the u. Then 1 over 2 root x dx is du. So that's just a straight substitution. And now I have a new integral that's u e to the u. Isn't that what you said you had at some point also? An integral u e to the u? Or no? You had something like it? Do I have any questions on that? 2 root x over 2 root x? I knew that I needed it. I threw it in there. What I needed was a 2 root x in the denominator to make this substitution happen. But I can't just throw it in there. I have to throw it on the top also. So, it's a trick. I mean, Now look at this integral here. This integral will not go with substitution. But it will go with what? Integration by parts. Because that's just like the integral x e to the x dx. And we know with integration by parts that if we do integration by parts once, it'll drop the power on one of them, right, and integrate the other. So when I look at u e to the u du, I know if I do integration by parts once, I'm going to drop the power on u, right? Y'all there? Okay, now I'm going to have to do it. I want to finish this out. So now I'm focusing my attention on this integral. Just remember that my final answer is going to have a 2 in front of it. Now when I do my integration by parts table, I cannot use u dv. Why? Because I'm already using u in the problem. So instead of ultraviolet minus voodoo, it's going to be something else. That's why I like the table, because the table is always going to put things exactly where I want them. I'm going to use, instead of u and v, w and v. So I'm going to say w here, dv here. What's w going to be for us? What's the variable that you want to drop down? U. dw will be du. Now, what was dv? E to the u du. And what's the antiderivative of e to the u? E to the u. So what is your VW going to be? VW going to be, right? What's this new integral going to be? That diagonal. E to the u du, which you can integrate. So this integral becomes 2. Then ultraviolet, it's not ultraviolet, it's ultraviolet, which is really what? U e to the u minus VW, whatever. It's VDW instead of VDU. So integral e to the u du. Yes? Well, I'm going to have to integrate first. I haven't integrated e to the u yet. I'm getting a couple of looks of dismay. What happened to our what? In which integral? Here? Where are you talking here? You said e to the 4th, right? Those are all u's. Okay. W times v. So here is my w times v minus v times dw. You got it? The 2's going to, oh yeah, I didn't distribute 2. Thank you. Here, I'll save myself. There. So my 2 I haven't distributed. Give me a second here. Now, I am going to distribute the 2 through, but I also need to go back and say what was u. We did a substitution way in the beginning. U was the square root of x. So this is going to be 2 distributing square root x e to the square root x minus 2 e to the square root x plus a constant, which I could factor out a 2 e to the square root x and be left with square root x minus 2 plus c. Minus, what's that? Where's minus 1? Oh yeah, why did I put 2? Square root of x minus 1, thank you. Whoa. Where? You could leave the 2 out, yeah. Wow. So what do y'all think of that one? That one was a substitution, that very unnatural substitution, followed by integration by parts. Followed by substitution. Well, no, we didn't. Well, resubstituting. Yeah, can you believe it? It's over. That was the next one I was going to do. And this was the last one I was going to do. Show that this formula is true. It's called the reduction formula. So what I'm saying is that we're not done. We need a little bit more in this section. So we are going to need to pick up on Tuesday with a little more of this, and then we'll talk about the test. But really, it's not going to be like an entire day of let's just review. I mean, it's going to be mostly, me doing more integration by parts problems, some substitution, and our test is pretty much going to cover what we've covered. So there's nothing. Integration by parts is the last topic we'll cover. No, I haven't given you the integration by parts homework. That's what I was going to do right now. So I need to borrow someone's book because I left it in my office. Thank you. This is Chapter 6, Section 1. Page 316. I'm sure that I have the solutions to this out there, right? Someone's probably looked up the answers for 6-1, or they're out. I'm sure I did the odds or evens or something. You can do 1 through 29. Odd. And as I've said before, if you do the 2 through 30 evens, you're better. You're even better. But I would start with the odds, check them in the back of the book. I think I have the evens worked out already on the web. And then there's a few more that I will ask you, but we have not covered yet, so I'll put it in red. Number 35. Number 37. So we haven't covered those, so you might not want to try and do them yet, all right? Have a good weekend.
So, just a question. When
Yes.